Today I want to show you some part of our work with Maxim Kravchenko. It's my presentation about the homomorphisms of the Kronrod-Reeb graph of Morse functions on two spheres. Let's start with some definitions. Let M be a compact two-dimensional manifold and Dm the group of diffeomorphisms of M. Then there exists a natural right action phi, you can see this, of this group on the space of smooth functions of M, defined by the next formula. For F in C infinity MR denoted by S is a stabilizer with respect to the specified action. A smooth function F is called Morse if the following conditions are fulfilled. First, F takes constant values on the connected components of the boundary Dm, and second, each critical point of F is non-degenerated and is contained in each M. Homotopy types of stabilizer and orbits of Morse function were started in many articles, but the most important for me is articles Lee Maximenko, Kravchenko, and Maximenko E. Kravchenko. Let F is Morse functions and gamma F be a partition of the surfaces M into the connected components of the level sets of these functions. And P be the canonical factor mapping associating to each x in M the connected component of the level set F minus Fx containing that point. In doing gamma F with the factor topology with respect to the mapping P. So subset A will be regarded as open if and only if its inverse image P minus A is open in M. Then F induces the function F hat such that you can see it's well known that if F is Morse function with respect to this topology, gamma F has a structure of a one-dimensional C complex called the Kronrod-Reeb graphs, or simply we say graph of F.
It was really Kronrod who made this construction. Why do you call it?
Kronrod has a big paper about two functions and two variables. And he studied level sets of functions on a plane, and this construction was also, in some sense, appeared in his paper. And another, Reeb, French mathematician, he also has a paper about relations, and I don't know who started to call this construction.
Which year was the paper of Kronrod?
52.
So, the term, you introduced it?
Actually, this was proposed by Volodymyr Sharko. And so he motivated it because this is a Kronrod paper, and maybe people from the Soviet Union, they do not works of Kronrod at that time, and so he rediscovered almost at the time the same thing.
The vertex of this graph correspond to the critical connected components of the level set and to the connected components of the boundary of the surfaces. By the edge of gamma F, we will mean the open edge that is a one-dimensional cell. On the picture you can see some illustration. Denoted by H gamma F, the group of homomorphisms of gamma F. Notice that each element of the stabilizer leaves invariant each level set of F, and therefore induces a homomorphisms rho of the graph gamma F. Moreover, the correspondence H is a homomorphisms of groups rho. We use some examples.
What is G of H? Moreover, the correspondence
Rho.
that's rho.
Should be rho instead of G, yeah?
That has to be rho, right?
Sorry. Let also the idea is the class component of the identity map ID in the Dm. Put a stroke B group of diffeomorphism of M, preserving F and isotopic to identity map. And then let GF be the group of automorphisms of the Kronrod-Reeb graph induced by diffeomorphisms belonging to S stroke. And in return to our previous example, we can see that GF equal Z4. Index in the previous article, our Maximenko and Kravchenko automorphism of Kronrod-Reeb graph of Morse function on surface of compact surfaces, we described the structure of the class G of groups GF for all Morse functions on all orientable surfaces distinct from two spheres and two torus. It was proved that class GMR consists with the following class of groups P. You can see this definition of this class P. It's let P be the minimal set of isomorphism class of groups satisfying the following conditions. First, it's 1 in P, and second, in A and B in P, and M in M, then A product B and A rest product Zn in P.
Could you remind what is G sub F? That's the automorphism group of that graph, or what is G sub F?
Sorry.
G sub F, right? Yeah,
This?
Yeah.
GMR is the class of groups GF, where F is Morse function.
What is GF? That's automorphism.
GF is a group of automorphism of Kronrod-Reeb graph.
You induce it by diffeomorphism
Physics.
isotopic to the identity and preserving function.
But
This is a very special process. It's very special.
S stroke.
Sergei, a question to the previous. Can you show? Previous, yeah. So graph is finite.
Yes.
So number of automorphism is finite also.
Yes, yes.
Why do you have Z in the power of 4 or
It
something?
that's
should be
fine.
subscript. We just discussed this. This should be subscript.
I didn't
Maybe I
understand.
say just a few words.
Yeah.
Lena Kudryavtseva, she proved that the orbit of a Morse function, the orbit, is homotopy equivalent to the quotient of a torus by some finite group G. And this group, with respect to free action, and this group G is precisely this group which Anya considers. So this group acts on the torus, and so Lena Kudryavtseva from Moscow. Is Moscow. And actually, you see here in the previous talk by Yulia, we saw the class of groups in the. Yes, Next slide. What you see in the previous talk by Yulia, you see the rest product was in another form. That was a special corresponding to the non-effective action of Z on some. And here we have a standard rest product with respect to finite product. And so this group, in some sense, that is in some sense the finite part of the orbit. This is because of some importance of some motivation why they are studying.
The present talk is devoted to the case M equal S2. In this situation, gamma F is always a tree, and therefore all elements of the group gamma F have a common fixed subtree fixed G, which may even consist of a Unix vertex. We denote by G1 the class of groups GF where the number of elements of fixed GF equal 1, and the class G greater than 1 is a class of groups GF where the number of elements of fixed GF greater than 1. Then the class GS2 is the joint union of the class G1 and G greater than 1. Our main result gives a complete description of the class G greater than 1. And our main result is our theorem. They say let F is a Morse function on a sphere. Suppose that all elements of the group GF have a common fixed age E. Let X in E be an arbitrary point, omega equal P minus 1x, and A and B be the closures of the connected components of the complement omega. Then first we find that A and B are two disks invariant with respect to a stroke, and second that the restriction FA and FB are Morse function, and the last that the map phi defined by the formula is an isomorphism of groups.
So the problem reduces from sphere to disks, and for disks we proved this in previous paper.
And then you reduce to graphs.
No. That was class P, or that class P which I showed. This class of group. And if the set of fixed point has a fixed age, then that group is also belongs to this class, is a product of groups on here.
Here we prove that class GMR coincides with the class of groups P. As a consequence of this theorem, we have the next corollary, that class group G greater than 1 coincides with class P. The case of function from class G1 when fixed GF consists of a Unix vertex is more complicated. But we recently find that the class G1 includes of symmetry groups of convex polyhedra, that is finite subgroups of SO3, is one of these, Z, and D by N, H4, S4, F5.
Alternative groups, okay. A are alternative groups.
Yes.
And S4 symmetric.
Includes of symmetric groups of convex. Thanks for everyone who spent your time and waiting.
Thank you very much. Any questions from the audience? Yes, please.
I have a question to Sergey. Can you explain something about Kronrod? Who was Kronrod? Where he was?
He was Russian mathematician. Actually, I don't know much about.
He worked in Kyiv?
In Moscow, he solved some some problems. He had a paper about functions in two variables. It was like a Hilbert problem which was solved by Arnold about composition of functions, and he tried to do this for continuous functions. And he has a very big paper. But actually, it is a very interesting story because the name of this graph was introduced not by Kronrod, but by his co-author, who also invented something like some discrete some algorithm in computers at that time. Anderson Wilski. He worked with him. And also there is a paper, maybe it was 47, by Frank, topologist in dynamical system, where he rediscovered this graph and he called it Lyapunov graph because it increases along orbits. So this construction appears in many cases in situations.
So now you have considered the case of all sorts except for the sphere and the torus in your previous preprint, and now this is about the sphere. What about the torus?
And the torus will be a PhD dissertation
okay.
Bogdan. He will talk about. So this was more complicated case because of non-triviality.
But also this case where the number of fixed point is 1 is also like where the stabilizer is just empty. Yeah? It's
when fixed point is 1,
yeah.
you may have how to imagine a Morse function which has on a sphere, whose stabilizer has only a unique fixed point. You take arbitrary convex body, polyhedron, and you can construct a Morse function whose maximums are at the vertices, saddles are at the middles of the edges, and minimums are at the centers of faces. And you can construct a unique critical level set containing all saddle points. And in this situation, you will get a function. You will get Reeb graph will be something like this. So you have some edges to one direction, some edges to another direction, and one point.
Star, some GF star, develop. Ми назвали її джевелоп, це там, де вона складається, виходить з вершини зірки.
So there will be a unique critical level set, which is a unique point.
So maybe one more stupid remark. Reeb was a French mathematician, so his family name is, you should pronounce Reeb. This is English pronunciation,
Yes,
which is not correct.
I also ask something about the basics. Could you go back about this S prime of F? I forgot what that means. That's some subgroup of the.
This?
No. In the definition, yes. Yeah, this one. What is S prime of F? Here, the group of preserving.
Preserving M.
I assume because identity.
Yes.
So actually, all non-trivial part of this group is concentrated only on disks on a surface. So you take a surface, you have a Morse function, and you consider diffeomorphism preserving this function, but isotopic to the identity. That actually it is all non-trivial parts are concentrated only on disks and cylinders and Möbius bands, because all other part has negative error characteristic, and we cannot deform this surface inside all surfaces.
Right, but still, why did you not consider just all diffeomorphisms instead of its identity component?
This group actually, pi 0 of this group is isomorphic to the pi 1 of the orbit. So so it has pi 0 of this group is the same as the group which considered Euler, told just in previous lecture.
So can you also say something about the whole group of automorphisms of that graph, Kronrod-Reeb?
But maybe actually
But just
there is a paper which so previously there is a result by Kelly that every finite group is a subgroup of permutations. Then there is another result that every finite group is a subgroup of automorphisms of some graph. And then there is the idea to consider cellular partitions of surfaces and consider group automorphisms of them. And it is also by Markley and some other people, they prove that every finite group is realized as a group automorphism partition. And Lena Kudryavtseva and Fomenko, they have a paper where they realize these groups by Morse function. So you take Morse function, you take having one critical level set, and the